Hi, everyone. Welcome to This Week in Space Science. I'm Michael Baltimore with my good friend and the Executive Director of the Coca-Cola Space Science Center, Dr. Sean Cruz. And Sean, how are you today?
I'm good, Mike. Thanks for having me in again today.
Hey, we love it. We have an opportunity to learn about space science. Every time you come in, you've been coming in for a while. You've got a great show here. I'm happy to be a part of it. And today, we've got to talk more about exoplanets.
Yes,
now,
we do.
Somebody who's watching this show remembers that last week we talked about exoplanets. But we're not going to stop with that. We're going to keep going because there's been a great discovery, and you've got to tell us about it. So what's up with these exoplanets?
Well, there's probably, if you look back through the archives of this show, there's probably several episodes where we've talked about exoplanets.
That is true.
And that's simply because it's one of the leading cutting-edge areas of research that's really producing some very interesting results right now at this time in history. And it's kind of fun, honestly, to be living through and noticing right now that we're living in this time where exoplanets, finding planets around other stars, is one of the things that our generation of astronomers is really doing well. And you know, this period in history will be looked back on someday and said, you know, this will be the time when we went from not knowing about any planets outside of our solar system to knowing about thousands of planets outside of our solar system in a very short period of time.
Absolutely. And so these are the times that really we're mapping where these planets are located, and maybe sometime in the distant future we may take a trip to some of these things. Well, we'll just have to see on that. That's too far to speculate out on that.
Well, but you know, that is kind of the idea, right? That's
yes.
That's what we want to do, right? And how technically feasible that is right now,
Right.
that can be debated. But
Yes, that's true.
that's where the innate human curiosity aspect really lies in the story. Is if there are other planets, are there other life forms? And if there are other life forms, can we get out there and explore it and either measure these other life forms or meet these other life forms and sit down and have some Starbucks or something with some of these other life forms? We just don't know the answer to those questions, but yet those are some of the fundamental questions of humanity. Some of the things that I really think drive our innate curiosity about the universe. And so it's, again, it's an amazing time to be living in when we see all these exoplanet discoveries coming at such a rapid pace.
But they're not just finding them, they're really looking at these planets and measuring these planets in lots of different ways and getting information about these planets and whether they're suitable for life.
Yeah, exactly. They really are. And you know, and I'm not that old. If you're watching me out there, you can probably see I'm not that old. But when I began first teaching astronomy at the college level, we knew about no exoplanets, no planets orbiting any other stars out there. There were some speculations, there were some possibilities, but no confirmed observations. And now, especially with the story we're going to eventually talk about here today, we've really seen that explode to where we know about all kinds of those. And again, that's one of the most interesting things about this field is discoveries in this field are coming very quickly. Not only are we identifying the locations of many of these exoplanets, but we're also finding out, as you say, some very interesting things about individual exoplanets. We're being able to measure their characteristics and properties. One of the stories coming out just last week was water identified in the spectrum from one of these planets that was somewhat close to a habitable zone. So here you have you know, one of these planets orbiting another star that's in this area, special Goldilocks area called the habitable zone. We're going to talk more about that here in just a little bit, but it might actually have water in its atmosphere. Now, that doesn't mean there's necessarily water on its surface, but there's at least water vapor identified in its atmosphere. So these are the kinds of discoveries that are happening on the subset of exoplanets that were known up until this latest announcement.
Now, are these planets, and I want to jump ahead on this, maybe I'm asking this question too soon, but are these planets generally within our the Milky Way galaxy, or are they further out? So
no, these are planets that are identified around stars that are somewhat nearby. And we're going to talk about the method by which they're discovered, and you'll see why they have to be nearby. But they're reasonably nearby in our own Milky Way galaxy. What we have to do then is just apply statistics to try to figure out, you know, if we can identify a certain number right in our own neighborhood, how many are there in the broader Milky Way, and then how many planets would there possibly be given that same statistic applied to other galaxies. and then you come up with a truly huge number of planets. But again,
Well,
those are planets speculated. What I want to talk today about is planets confirmed.
Ah, okay.
Planets that have been confirmed to be orbiting other stars. Measurements have indicated with no doubt that these planets are in existence, that they're there, and we know about them for sure. And that's really the big story today. So do you want to hit this headline, or do you want me? I'll let you roll this headline off.
No, I'm waiting for you to hit this one. This is a really nice headline, by the way, and it all happened. I will take some of it. One day it happened.
All in one day.
All right.
So an announcement came from the Kepler Space Telescope team. They had applied a new method of analysis to their data, and they realized that they were able to confirm with their own data the existence of 715 planets
Wow.
in one day, in one announcement. 715 new worlds.
Sounds like a lot in one day. I don't
It's a
know
whole
how
lot
you
of
gather
planets
that
for one
data
day.
and work with it. Yes.
So certainly there has been no other day in the history of hunting and identifying planets than this day, where you've had so many planets identified on the same day. Now let us remember that it was just back in 1930 when Clyde Tombaugh at the Lowell Observatory in Flagstaff, Arizona, came out with a very huge announcement in the world of astronomy, which was the discovery of one additional planet in our solar system, and that was Pluto. And then later on, we allowed Pluto to even be downgraded from that. So Pluto's not even a planet anymore; it's a dwarf planet. But you know, just to give you some perspective, that really changed the way society looked at our own solar system. Was the discovery of this one new planet, the planet Pluto. Here today, we're talking about the discovery, or the announcement of the confirmation of the existence of 715 new planets. Now, that takes the total number of planets that we know about from about 900 and in the 80s up to 1,700 planets in one announcement. So that's a tremendous increase in the number of planets that we know about out there in our own galaxy, actually, in the Milky Way galaxy, but that we know about overall. So we went from in the 900s to 1,700 in one single day with one single scientific announcement.
That is amazing.
I want to get that point across. Just to say that's how earth-shattering of an announcement it really is.
Well, how many people were involved in that? By the way, you must have teams of people, because one guy with a telescope in the lab would not be able to pull this off. So it must have been teams, and maybe even around the world too.
Yeah. There are literally dozens and dozens of scientists and technicians and astronomers who are working all together as a team on what they call the Kepler Space Telescope team. And so let's talk about the basic techniques, and we'll talk about how exoplanets are normally identified, and then how this group was identified. So there is a telescope up there called the Kepler Space Telescope, and it's out in space, which means it's above Earth's atmosphere. And the Kepler Space Telescope is able to watch a fairly wide section of the sky, a cone on the sky. And in that cone, it can watch all of the stars that it can see in that cone of the sky. And it takes pictures of those stars, and it looks for any of the light from any one of those thousands of stars varying. If it can come up with a variation in the brightness of the light from any of those stars relative to the other stars, it knows that something changed the light of that star. Now, there's a lot of things that can change the light of stars. You could have another star pass in front of it, or you could have the star itself varying. So we call those binary stars or variable stars. So you have to rule out that that's what you're seeing. But after you've ruled that out, you say, well, this is at least a candidate for an exoplanet, because then what's left as a possibility is, if that star varied for reasons that are not because it's a binary star or not because it's a variable star, that means it must have a planet or set of planets orbiting around it, and one of those planets moved just right to where it was in the light path between that star and the Earth. That is what the Kepler Space Telescope is uniquely good at doing. And Kepler Space Telescope was monitoring 150,000 stars, watching for evidence of that kind of a phenomenon. And out of that grouping of stars, remember, it had to be lined up just exactly right for Kepler to see it. Out of that grouping of stars, Kepler was able to identify over 4,000 of those stars, which it called candidate stars for possible exoplanets. Okay, so that's what Kepler was good at. It was good at getting the ball to that stage to say, hey, we've got these, few thousand stars now that we think the light is varying in such a way that it would cause us to believe that there's an exoplanet out there. So then what would happen is either the Hubble Space Telescope or teams of telescopes on the ground would go back and observe that star in more detail and try to figure out whether or not the variations in light from that star were being caused by planets orbiting around it. So that was kind of the procedure. And actually, honestly, given the number of stars, potential candidate stars that Kepler had identified, that's a pretty slow procedure. That's kind of like trudging through the mud, right? So the scientists at the Kepler Space Telescope group figured out a way to apply a statistical model, and it's got a neat name. It's called validation by multiplicity. Validation by multiplicity. We're going to talk about what that means. But they figured out a trick to be able to identify those candidate stars that had to have solar systems around it. So that was the validation part. We're going to be able to confirm for sure that these stars have planets around it. They did that by multiplicity. What does that mean? Well, that means that there are more than one planet around those stars. And here's the thing. Once you've ruled out that the star is a variable star, or that the star has a companion star, then any variation in light probably is caused by a planet, but you don't know that until you have the confirming observations. Well, maybe that star flickers more than once. In other words, maybe that star flickers in such a way that lets you know that multiple planets are moving by. And it turns out that in our solar system and in our models of how solar systems form in general, planets tend to pancake down into a plane as they orbit around their parent star. So if one planet is going in front of the face of the star, chances are that other planets will be passing very close to that plane along our line of sight of observation. So what the team at Kepler did is they went and looked at their data and they figured out all of those stellar candidate stars for potential exoplanets that had multiple variations. In other words, multiple things passing in front. And by statistics, that really can't be a random collection of orbiting stars in a star grouping or anything like that. That has to be a solar system. So that's the verification by multiplicity. If they have multiple sources causing that star to dim and vary, that can only be caused by a solar system, and therefore they're calling that confirmed. They're calling that confirmed in over 300 cases of those stars that they have multiple planets around them, which leads to the number 715 new planets being confirmed by this great statistical technique and from that fantastic data from the Kepler Space Telescope.
Well, the Kepler telescope is an amazing piece of equipment. We're going to talk about it a little bit later in this show that it had some problems.
It did have some problems,
We'll have to come back to that. But all right, so what about the size of these planets? Do we know anything about the size of them?
Well, obviously, and you can see why this would be true by the technique by which they find these. The bigger the planets, the easier they are to identify.
Right.
So Kepler is going to tend to find a lot of large planets. However, some of these variations are occurring from Earth or close to Earth-sized planets. In other words, planets that are not a whole lot bigger than Earth, right? So out of those new 715 planets, 106 of them are less than 1.25, in other words, 1.25 times the diameter of the Earth, which means they're very close to Earth-like planets. So now think about that. Of that data set, we're able to identify and say 106 new Earths out there, right? Orbiting around other stars. So these are not planets, big gas giants like Jupiter or tiny planets like Mercury. They're roughly the same size as our own Earth. And again, think about the whole business about life as we know it, life as we understand it. We can see how life as we understand it might be present on a planet that has roughly the same size as the Earth, because it would have roughly the same gravity and there would be other properties, right? So one of the things that we would need in order to be able to identify whether or not a planet might support life as we understand it and life as we know it is if that planet is about the same size and characteristics of our own Earth. 106 new candidates for Earths orbiting around other stars out there. That in itself another major interesting accomplishment from this Kepler data, from these Kepler observations.
And a big increase too, because before that, I imagine the number was very small.
Yeah, it was not anywhere near that. It was a dozen or so.
Okay.
Earth-like planets, and so this has really catapulted that number forward. And as you say, that's very important. Now, that, as it turns out, is not the only important aspect of whether that planet could support life, because you might have a planet the size of the Earth. But think about it, if it was orbiting a star that was similar to the sun, think about that planet being way out there by Pluto. Well, what would that mean? Well, that would mean it's just way too cold out there for this precious stuff called liquid water to be able to exist on the surface of that planet. And again, if we're going to talk about life as we understand it, probably going to need the presence of liquid water on that surface. So planets way out there in the outer parts of those solar systems, far away from their parent star, would be just too cold to support liquid water, and so too cold then to support life, at least as we understand it.
And of course, too close, it's going to be too hot.
Exactly. That's the other side of the coin.
Yes, you've talked on this show about the Goldilocks zone.
That's right.
I think that's where you're going next.
but
it has to be that zone right in that area.
Yeah. By same account, some of these exoplanets that have been identified are maybe 10 times closer to their parent stars than Mercury is to our sun. So think about that. They orbit within just a few days, and they're so close to their parent star that they would be ridiculously hot. So that's the other side of the coin. It's just too hot. If you want a habitable planet, you can't have it too hot and you can't have it too cold. You have to have it just right. And that's where this whole business of a Goldilocks zone comes from. That's where that phrase evolves from. It's because you want it in what they more technically call the habitable zone, a region in a distance from a star where liquid water could exist on the surface of that star. Now, I think we have a graphic of a few potential habitable zones, because it's not just about the distance alone, it's also about how hot the star is.
Right.
And as we look at this graphic from NASA, we'll see some colors on these graphics. You see 3 different stars, a blue one at the top, that's the big hot star, a yellow one in the middle, that's kind of sun-like stars, and little kind of orange reddish colored star at the bottom, that's the cooler stars that are cooler than our sun. If we look at the rest of the colors of that graph, you're going to see a region in near the stars that are red in color. That's just the region where it's just too darn hot for liquid water to exist. It would vaporize, boil off, and you wouldn't have any water on the surface. Then you see the blue parts of those Frisbee disks up there, and those are the areas around those stars where conditions would just be too cold on a planet for liquid water to exist. The water would freeze down to the surface of the planet, and you would have ice, but you would not have liquid water oceans. In between the red and the blue, you're going to see some green rings. And those green rings are what we would call the habitable zones. Those are the areas inside of which, if a planet was in that orbit, it could potentially be in that just right temperature range to have liquid water existing on its surface. Notice how much bigger the habitable zone is around the hot star. That's a lot bigger Goldilocks zone. So you might be thinking, well, gee, maybe we should go out there and look at those hot stars. Well, the problem with hot stars is this. Number one, they don't live nearly as long as our own sun.
Okay.
So even if life could get going there, it wouldn't have very long to hang around before that star started doing some crazy things and maybe run out of fuel and explode. The other thing is, those hot stars tend to put off a much more intense set of both gamma rays and X-rays and even ultraviolet that would be very harmful for life to exist. So even though you might have a planet that has liquid water on its surface, the life on that planet would have a very hard time surviving in the radiation environment around those very hot stars. So we tend to be more interested in the sun-like stars and the cooler stars and what planets might be in their habitable zones. Those are the more fertile fields to go out and look for planets in habitable zones that might potentially have the possibility for life existing on their surfaces.
Okay. All right, that makes a lot of sense. I appreciate that graph because it gives us a real clue about what you're talking about on these habitable zones. Okay.
Well, here's the beauty about the habitable zone planets. So you might think, well, this must have really increased the number of planets that we know about that are both Earth-like and in the Goldilocks zone, and that's true. So prior to this, there were 4 somewhat Earth-like planets that were also in habitable zones. Now out of this data set, there are 9 known Earth-like planets that are also in habitable zones. That is a dramatic increase in the number of places that we should go and look for, take a closer look at those exoplanets, see if we can get more data. We should look for water vapor in the atmosphere of those planets. We should try to determine the temperature conditions on those planets. We should try to figure out what the mass of those planets really is, so we can maybe try to better understand the gravity conditions on that set of planets. And mind you that the planets that we added in that particular group, they go all the way up to twice the size of the Earth. So their gravitational fields would be significantly stronger than Earth's is here. So you imagine weighing a whole lot more on those planets than we would weigh here. But anyway, we still want to investigate the properties of those planets and really understand them, because those are places where life of some kind has maybe the best chance, at least that we know of establishing itself and really being able to survive in those kinds of conditions.
This has been an amazing piece today on this broadcast. You've talked about 715 new worlds in one day. It's hard to get over that.
It's really an interesting number.
The discovery, a piece of it. I know there was a graph at one point. I don't know if we have that slide, but you were showing how the discovery over a period of time and also at that one day. It is absolutely amazing.
So NASA put out this very interesting table, and it shows on the bottom of the graph, it shows the years in which planets have been discovered. Look at 1996. 1996 was the actual year where the first exoplanets of any kind were discovered, and those were found around neutron stars. So those were found around dead stars. It wasn't until 1998 that planets were discovered around stars other than those neutron stars. So anyway, there is a graph of when exoplanets have been discovered, and as you can see, the exoplanet discoveries kind of trickled in throughout the last decade and a half, all the way up till about 2007, 2008, where we started to get really good at it. And then that Kepler Space Telescope came online in 2010. And on this graph, you can see that as the orange bar increases. And you can see that Kepler got very, very good very quickly at identifying exoplanets, or at least identifying exoplanet candidates that were then later confirmed by ground-based telescopes. But look at the year 2014. Look at that spike in the yellow. That's this whole new subgroup of exoplanets that were discovered by this technique of validation by multiplicity. And now, wow, in just 1 year, or really in just 1 day, as we've said, in just one publication of research data, that number of exoplanets has literally exploded, and we get that giant count of exoplanets here in the modern era.
There we go. That table is amazing right there. It really makes the point. But we've got a problem. We've got to come back and we've got to talk about Kepler itself, because as we talked about on this show before, the Kepler telescope has problems.
The Kepler telescope had a pretty significant mechanical failure last summer, the summer of 2013. And so think about this spacecraft out there. In order for Kepler to be able to get the data from these stars to look for these tiny variations, that telescope has to point itself and maintain its orientation in space to a very high degree of precision. It has to point exactly in the same place to make sure it can observe the same stars in the same manner. Well, that requires on board what they call reaction wheels, which are basically their high-tech gyroscopes. And those gyroscopes are spinning in 3 different orientations. And with those spinning gyroscopes, that lets the telescope know what its attitude is in space. All the angles, yaw, pitch, and roll, its attitude in space, so that it can point itself correctly and maintain its orientation on that star field and gather that great data so we can explore the universe. Well, the problem is the reaction wheels aboard Kepler began to fail. First 1 failed, and it was down to 3, but with 3 reaction wheels, it can still locate its orientation in space. But then last summer, another reaction wheel failed, and it went down to only 2. And that means it could only point itself successfully in 2 axes, but it couldn't point itself in the 3rd axis, and that caused the telescope's pointing overall to fail, and so Kepler basically went offline. But the scientists are being very clever, because the telescope itself, it's still working. the mechanics of the actual instrument are still working. It's the spacecraft portion of it that's not working. So the technicians and scientists thought, how can we get this telescope back to life? We'd love to be able to get the spacecraft side of this telescope at least back to life enough to be able to function. Well, they came up with something called Kepler's Second Light Project, or they're calling it K2, which is actually a nickname I use in my astronomy class for Kepler's second law when we study that. But and my students might know that. The rest of you, it's not very interesting. Anyway,
there will be a test.
There will be a test later.
Yeah, that's right.
K2, the name of this project, Kepler's Second Light. What they want to do is they want to be able to use the solar wind pressure from the sun to push against the spacecraft so they can hold it in a certain orientation where the solar wind pressure from the sun is providing enough pressure that it will help maintain the orientation of that telescope in one axis. And then they can maneuver it in the other two axes. And here we see kind of an infographic to show how that would work. And the best part of this to see is in the upper left-hand corner there where you see the sun, you see these kind of sun's rays demonstrating the direction of the solar wind there, pushing on the spacecraft, providing that pressure, and that's what's going to help orient it in at least one axis so that then the two reaction wheels that are still working can hold it in the other axis. Now, this is still not providing a very accurate pointing, but what it would allow is for the telescope at certain orientations, that whatever direction it happens to be pointing, it could at least photograph the stars that are in that direction, right? And so then you can use that geometry to reobserve the same field of the sky every time it orbits around the sun, and you could piece together those observations, and you could have Kepler working at some level. So this is a much reduced functionality of the telescope, but yet a functionality nevertheless. And so they're still going to be able to use the high-tech instrumentation and electronics inside the telescope portion of it, even though that spacecraft is having a pretty serious technical malfunction.
Yeah, absolutely. Well, that's a very clever idea for them to use that. And
Very interesting idea.
Tip of the hat to those guys for figuring that out. All right, we're coming to the end of our show, but we have one more area to explore, and this is completely different than what we've been talking about with the Kepler.
Has nothing to do with Kepler.
And the 715 new planets.
Yeah, has nothing to do with the 715 new planets.
All right, this is something about an asteroid
stars.
and a moon.
This is our own moon.
Our own moon.
Yep.
Okay, well,
this
good.
This is simply us inserting a story at the end of our show.
Come on.
Because it's just cool.
All right,
so this
there
is
you
just
go.
neat. So imagine just randomly looking up at the moon and you're observing the moon. People do this on any given night, and all of a sudden, something large comes in and slams into the surface of the moon at a very high rate of speed, and you have your video cameras on, and you capture that moment.
That's never my luck, but I wish it were.
It's never my luck either,
Yes.
but here it is. And okay, so you're looking at this photograph, you're gonna see gray on gray, but look for kind of a gray circle edge at the top of the photograph. Then look at the bottom of the photograph, you're gonna see a date and time. This was back in November of last year. And then you're going to see a little arrow pointing a little bright light right there.
Okay.
Well, it's just been confirmed that that bright light was indeed an asteroid impact. And this was captured by a fellow by the name of Jose Mediado. Sorry.
Okay.
Had that name down before the show.
No,
I don't
that's
know why I'm
quite all right.
slaughtering it now.
No, that's
sorry,
okay.
Jose Mediado. And Jose Mediado is a Spanish astronomer, Huelva University. They actually have a set of cameras that are watching the moon all the time to try to capture these kinds of events. And so this was an electronically triggered set of video where they sent out an alarm saying, "Hey, we think we've captured something."
A little motion detection.
It was kind of like a brightness detection on the video camera.
Okay.
So this is the purpose of their instrument. But they did happen to capture an impact in the Mare Nubium region of the moon. Something about the size of a refrigerator, moving at something around 38,000 miles per hour, came in and slammed into this place that they call Mare Nubium up on the moon, and it blew up basically, leaving a 130-foot crater. Now this thing was probably around on the order of 1,000 pounds, a big rock, about 1,000 pounds, about the size of a refrigerator, slamming into the lunar surface. Here we're seeing video of the time, and again, if you watch for the blue arrow down there, you see that bright flash. Well, the interesting thing about that bright flash is it doesn't fade out instantly. it's on there for a while. So here's a repeat of the video. Boom, there's the flash right under the running clock. And then you see that bright spot fades out over time. That's because when that object hit, it exploded with about 15 tons of TNT equivalent explosive power. So that's a pretty good explosion.
Yeah,
that's going to
really
heat up
is.
a whole lot of material right there on the surface. And what we see here, this is a set of photographs taken from that video of that spot. And this is a time sequence. So the first one's in the upper left-hand corner. The end of the time sequence is in the bottom right-hand corner. So if you kind of follow along reading from left to right, you'll see it's big at first and then it shrinks. But it shrinks rather rapidly at first. But then it stays about the same size. So that explosive area, that superheated crater, stays about the same size for almost the rest of that 8 minutes of video over which they could still see the spot. The reason that they think that that's probably true is once that explosion occurred, once that impact occurred, that threw out all of that material in what we call the ejecta blanket, that material was superheated. What happens when you heat up silicon? Well, you can make glass, right? And that glass stays very, very hot for a while. So this would have been impact glass on the moon. You heat up the soils in the moon's surface, it throws out this material, and then you have this super hot, glassy-like material laying all over the surface of the moon, glowing red hot for a long period of time. And that's why that little spot was visible for several minutes after that impact, because of all that lunar glass laying over the surface due to this new impact crater on the moon. So Jose Mediado from Spain, congratulations on a fantastic observation. Congratulations on it being confirmed that you really did see an asteroid impact, and really neat stuff. And it kind of shows you that we live in this shooting gallery environment in the inner part of the solar system where these kinds of events can take place.
Yes, and on this show we've talked about these asteroids crashing in and even crashing on Earth with the Russian asteroid not that long ago.
Exactly.
We need to keep an eye on space. I'm glad you're here every week to keep us informed about what's going on, but we need to all look out there.
Yeah.
Maybe we need to,
it turns
keep an eye
out
on
right
this
here at
thing.
Columbus State University, one of our faculty members by the name of Andy Puckett, his specialization in research is to monitor the orbital paths of near-Earth objects or near-Earth asteroids. So he's getting some of our students in the Earth and Space Sciences Department right here at CSU involved in that kind of research and using the telescope at the Coca-Cola Space Science Center to be able to do that. So those are kind of cool things that are evolving here on our campus with the addition of a brand new faculty member last year. So we're excited to have Andy here.
Well, we're appreciative of that. And thank you, by the way, for coming in every week here on This Week in Space Science. This is a show that informs us about what's going on this planet and in our solar system and the Milky Way galaxy and beyond. Sean, thank you so much for coming in today. Ladies and gentlemen, thank you for being with us here on This Week in Space Science, Twiss as we call it. Find us here every week on Columbus State Television. I'm Michael Baltimore for Sean Cruz, and we'll see you next time.